Welcome to the deep dive. We take your sources, cut through the noise, and really try to find those genuine aha moments.
That's the goal.
Today we're doing a deep dive into something absolutely foundational to, well, everything digital, the transistor. And we're going straight to the source. William Shockley's 1956 Nobel lecture. It's called Transistor Technology Evokes New Physics.
Yeah, and it's a fantastic read because Shockley, one of the inventors, he makes this really compelling argument
Just that.
that applied research aiming for something useful isn't some lesser form of science. He really believed passionately that chasing practical devices could directly lead to fundamental breakthroughs.
A philosophy that really shaped Bell Labs where all this happened.
Absolutely. It was baked into the culture there.
Okay, so for you, our listener, what's our mission today? What are we trying to uncover as we unpack this incredible lecture?
Well, we want to go beyond just the invention itself. It's not just what the early physics of transistors involved, but how the very practical drive, trying to build things like electronic telephone switching.
Which sounds almost quaint now, but was revolutionary then.
Exactly. How that practical need pushed these brilliant minds to ask much, much deeper questions about how the universe actually works at this tiny scale.
So we'll look at things like the imperfections that turned out to be crucial.
Yeah, those imperfections, these ingenious experiments they devise to actually see how electrons and holes behaved.
Things you can't just, look at.
Right. And then the elegant simplicity, really, of the PN junction, that structure that's, well, it's the absolute backbone of all modern electronics.
Okay, let's start with that big idea then.
Mhm.
Practical goals driving fundamental research. Shockley makes a pretty strong case right at the start.
He does. It's quite a statement for the time. He directly challenges this notion that having a practical goal somehow degrades the quality of research.
Like it's somehow less pure.
Exactly. Instead, he points to places like Bell Labs, where the leaders, people with strong science backgrounds themselves, they got it. They understood fundamental research had immense practical value. It was like a core belief.
Asking the deep questions could solve real problems.
Precisely.
And he shares a personal story, too, doesn't he, about how this influenced him.
Yeah, it's a great little anecdote. He talks about a chat with a research director, Dr. Kelly, about this really futuristic idea back then, completely electronic telephone switching.
Right. No moving parts.
Yeah. And Shockley wasn't even working on vacuum tubes, which was the obvious path then. But that conversation, that vision, it kept him, quote, continually alert for possible applications of solid-state effects.
So that big engineering target kept his mind open.
That's it. That clear, practical vision acted like a sort of North Star. It sparked his later work on transistors. It shows how a big, ambitious goal can really focus scientific curiosity.
So for Shockley, the label pure science, applied science, it wasn't really the point.
Not at all. It was the outcome. He put it very clearly. Quote, to me, it is more important to know if the experiment will yield new and probably enduring knowledge about nature.
That's the key.
If it is likely to yield such knowledge, it is, in my opinion, good fundamental research. It really gets to the heart of it, aiming to confer the greatest benefit on mankind, like Nobel wanted, impact over category.
Okay, here's where it gets, I think, really fascinating and maybe a bit counterintuitive. Shockley dives into these fundamental imperfections, things that are absolutely critical for semiconductors to work. We know about electrons and holes, but he talks about donors, acceptors. And he uses this brilliant analogy.
Yeah, the analogy to water solutions is really insightful. He says, okay, think about pure water. It naturally has a balance of hydrogen ions and hydroxyl ions, right?
Right, H plus and OH.
Well, a pure semiconductor is similar. It has an equilibrium between electrons, which are negative, and these things called holes.
Which are like missing electrons, positive charge carriers.
Exactly. So pure semiconductor, pure water, balanced. Then, to make it useful to control its conductivity, you add tiny amounts of impurities.
The imperfections.
Right. So an N-type semiconductor is like adding a base to water. You add donors, impurities that donate extra electrons, more negative charge.
Okay.
A P-type semiconductor is like adding an acid. You add acceptors, impurities that create more holes, more positive charge.
Makes sense.
But here's a key difference he points out. Unlike ions floating around in water, these donors and acceptors in a semiconductor crystal are fixed. They're tied in place.
So they don't move around.
Right, which
Yeah.
makes their electrical effect much more stable and predictable. Very important.
And then he introduces this fifth imperfection.
Yeah.
And it has this amazing, slightly ominous name.
Yes, deathnium. Sounds bad, doesn't it?
It really does.
But its role is actually incredibly important. He compares it to a catalyst. In the semiconductor, deathnium basically speeds up the process where electrons and holes find each other and recombine.
They annihilate each other, in a way.
Sort of, yeah. They cancel out, returning the material to its normal equilibrium state. Deathnium makes that happen much, much faster.
So its job is just to speed up the return to normal.
That's it. He gives an example. Imagine you shine light on a germanium crystal.
Oh, yeah.
That light creates extra electron-hole pairs, makes the crystal more conductive for a moment, photoconductivity.
Right.
When you turn the light off, those extra pairs need to recombine. How fast they do that is called their lifetime.
Okay.
And, Shockley notes, experimentally, you could have two germanium crystals that look identical, same purity basically, but one might have a lifetime of a millisecond and the other just a microsecond.
Wow.
Yeah, 1,000 times faster. That huge difference couldn't be explained just by the main impurities. It needed something else acting as this recombination catalyst. That's deathnium. It could be tiny amounts of copper, nickel, or even just disorder in the crystal lattice itself.
So does this deathnium change the actual number of electrons and holes when everything's settled at equilibrium?
That's a crucial question he addresses. And the answer is no. It doesn't change the final balance. Deathnium dramatically increases both the rate pairs are generated and the rate they recombine.
It speeds up both sides of the equation.
Exactly. So the equilibrium concentrations, the final number of electrons and holes stays the same. Deathnium just gets you to that equilibrium much faster. It's like a super efficient referee, not changing the rules, just ending the play quicker.
Okay, let's shift gears now. From these fundamental concepts, almost philosophical points about imperfections, to the actual experiments, the groundbreaking stuff that showed how semiconductors really behave. Shockley highlights three key ones. Let's start with the field effect.
Right, the field effect experiment. This one started with a very practical goal. Shockley was trying to invent a semiconductor amplifier.
The Holy Grail.
Pretty much. The idea was simple, conceptually anyway. Take a thin slice of silicon or germanium, put a strong electric charge nearby like one plate of a capacitor. That field should push or pull the electrons and holes inside the semiconductor, changing its conductivity.
Makes sense. Apply a field. Change the resistance.
Yeah, but it didn't work. At least not at first. The initial experiments, he says, yielded negligible effects.
That must have been incredibly frustrating.
Oh, absolutely. But that failure was actually a huge clue. It led John Bardeen, another key figure, to propose his theory of surface states.
Surface states.
Yeah, basically electrons getting trapped right at the very surface of the semiconductor. These trapped charges acted like a shield, blocking the external electric field from getting inside and affecting the bulk conductivity.
So the effect was happening, but it was being screened off at the surface.
Exactly. The breakthrough came when they tried the experiment again, but this time at really cold temperatures, liquid air temperatures.
Why cold?
Because the cold effectively froze those surface states in place. It immobilized them. Suddenly, the external field could penetrate. They did see the change in conductivity, a positive result.
Wow. So the failure led directly to understanding the surface, which then led to success.
Precisely. And that understanding was crucial. It eventually paved the way for the very first type of transistor, the point contact transistor.
Okay, so that opened the door. Then the investigation into how these carriers, the electrons and holes, actually move really took off.
Yeah.
Which brings us to the Haynes experiment, sometimes called the drift mobility experiment.
That's right, J.R. Haynes experiment. And yeah, this was very hands-on. To really get a handle on transistor action, they needed to know exactly what happens at that critical point where a metal wire touches the semiconductor.
The contact point.
Right. Shockley explains it's not just about electrons flowing out of the semiconductor into the metal. For a good contact, something else happens too, something vital.
Which is?
The contact actually injects minority carriers into the semiconductor. So for N-type germanium, which has lots of electrons, a good contact injects holes.
Positive carriers.
Yes, and this injection of minority carriers, that's what dramatically changes the semiconductor's conductivity locally and makes amplification possible. It's not just draining the majority carriers.
Okay, so how did they prove this injection was real? And how did they measure how these injected carriers moved?
Right, that's the beauty of the Haynes experiment. Imagine they took a long, thin bar of N-type germanium.
Okay.
At one end, they put an emitter point. They used a pulse generator to make this emitter inject a tiny burst of holes into the bar like a little puff of smoke.
A pulse of positive charge.
Exactly. Then they applied an electric field along the length of the bar, a sweeping field. This field would grab those injected holes and literally pull them down the bar.
Like dragging the puff of smoke along.
Precisely. And at the other end, or maybe at points along the way, they had a collector point connected to an oscilloscope. This collector would detect when the pulse of holes arrived.
So they could actually see the pulse travel.
They could. The oscilloscope trace would show the pulse arriving after a certain time delay. It was ingenious. They could directly watch and measure two things.
What were they?
First, the drift, how fast the center of the pulse moved down the bar under the influence of that sweeping field. They found if they doubled the distance, it took twice as long. Doubled the field, it took half the time. Clear drift.
Okay. And the second thing?
Diffusion. Just like smoke spreads out, that pulse of holes would naturally spread out as it traveled. They could measure how much wider the pulse got over time.
Wow. Direct measurement of both drift and diffusion.
Yep. And they could prove they were tracking holes because if they reversed the sweeping field, the pulse wouldn't arrive at the collector. It confirmed they were tracking these positive carriers injected by the emitter.
And did this lead to some fundamental physics insight beyond just seeing it happen?
Oh, absolutely. This was huge. From these careful drift and diffusion measurements, Haynes and his team calculated the mobility, how easily carriers move in a field, and the diffusion constant for both electrons and holes in both silicon and germanium.
Okay, getting numbers on it.
Right? And when they looked at the ratio between the diffusion constant D and the mobility, they found something remarkable.
Well, what was it?
The ratio D over oin consistently came out to be about 25 millivolts, or more precisely KTQ at room temperature.
KTQ, that sounds familiar. Thermal energy per unit charge.
Exactly. This is the famous Einstein relationship. Finding it held true for these carriers in a semiconductor was profoundly significant. It directly linked their random thermal motion, diffusion, to their response to an electric field, mobility, and confirmed fundamentally that these drifting holes and electrons really did possess the elementary electronic charge, Q. It wasn't some other weird effect.
That's a beautiful confirmation of basic physics principles right there in the crystal.
It really is a cornerstone result.
Okay, so we've got field effect, drift, and diffusion. What about the third key experiment area? Hot electrons and Ohm's law.
Right. This investigation was driven again by a practical need, making transistors that could amplify signals at much higher frequencies, faster switching.
Always pushing the speed limit.
Always. Shockley had an idea, which it turns out someone else, Cromer, had also thought of, about what happens when you apply a really strong electric field to the carriers.
Stronger than in the Haynes experiment.
Much stronger. The basic idea is, okay, an electron or hole moving through the crystal lattice keeps bumping into the atoms, losing energy-generating heat, or what physicists call phonons.
Like friction, basically.
Sort of, yeah. So if you crank up the electric field really high, trying to make the carriers go faster and faster, they start hitting the lattice more and more violently. They can't just keep accelerating indefinitely. Their drift velocity starts to saturate.
They hit a speed limit because they're losing too much energy.
Exactly. They get hot, meaning their energy is much higher than the normal thermal energy of the lattice around them. And experiments, like those done by Ryder that Shockley shows, clearly demonstrated this.
What did they show?
They showed that the current density, which depends on the drift velocity, did not increase linearly with the electric field at these high fields. It started to level off.
So Ohm's law breaks down. Current isn't just proportional to voltage anymore.
Precisely. Ohm's law, that nice, simple, linear relationship, fails at high fields. This non-linear behavior, the carriers getting hot and saturating, it's not just a theoretical curiosity.
Yeah.
No, it's absolutely crucial for accurately calculating how semiconductor devices will actually perform, especially for designing transistors that can work efficiently at very high frequencies. You have to account for these hot electron effects.
Okay, so having nailed down these fundamental carrier behaviors, field effect, injection, drift, diffusion, hot electrons, the next big step was building more predictable devices, better than those early, somewhat finicky point contact transistors. This led to focusing on the PN junction.
Yes, and this was a really important strategic decision at Bell Labs. Point contacts, a sharp wire touching the semiconductor surface, they were just too complex, too hard to understand exactly what was happening right at that tiny point, atom by atom.
Hard to model, theoretically.
Very. But PN junctions, where you change the impurity type within a single continuous crystal, that seemed much simpler, much more amenable to theoretical analysis and prediction. Plus, Shockley had already conceived the junction transistor in 1949, which relied on these structures, so there was a clear path forward.
Right. So how do they actually make these high-quality junctions
Mm-mm.
and the super pure crystals needed for them? Because you mentioned earlier, attempts weren't great.
Yeah, this is another fantastic example of practical needs driving innovation in materials science. The early attempts to make junctions, Shockley admits, were not theoretically satisfactory. They had issues with cleanliness. They didn't even realize how damaging tiny traces of copper could be back then.
So they needed better materials first.
Absolutely. The real turning point came when management, particularly J.A. Morton, pushed hard for a program to grow large, perfect single crystals of germanium.
Not just little chunks, but big uniform crystals.
Exactly. And G.K. Teal and J.B. Little developed the pulling method. You start with a tiny seed crystal, dip it into molten germanium, and then slowly pull it upwards while rotating it.
And the crystal grows as you pull it out.
Yeah, it solidifies onto the seed, creating a large, almost perfectly structured single crystal. And crucially, by adding the right impurities, donors or acceptors, to the melt at the right time during pulling, they could create the PN junction directly within that growing crystal.
That's incredibly clever, growing the device structure itself.
It was a huge leap, but then came another, arguably even more important development for purity: zone refining.
You mentioned this earlier, the vacuum pump.
Yes, invented by W.G. Fan. It's based on a simple principle. Most impurities are actually more soluble in molten germanium than in solid germanium.
They prefer to stay melted.
Right. So Fan devised a way to pass a narrow molten zone repeatedly along a solid rod of germanium. As the zone moves, it kind of sweeps the impurities along with it, pushing them towards one end of the rod.
Like a squeegee pushing dirt.
That's a great analogy. And after multiple passes, you end up with one end of the rod incredibly pure and the other end concentrated with all the junk.
And how pure are we talking?
Astonishingly pure for the time. Maybe one impurity atom for every 10 billion germanium atoms. Unprecedented. This technique was absolutely essential for making predictable, high-performance transistors.
Okay, so now they have these ultra-pure crystals, and they can create these PN junctions inside them. What does that junction actually look like, electrically speaking?
Right, so imagine you have this perfect crystal, but on one side it's N-type, excess electrons, and on the other it's P-type, excess holes. Even though mechanically it's seamless, electrically there's a dramatic boundary. Now, basic physics says things tend to spread out, right? Diffusion. So the electrons would naturally want to diffuse over to the P side, where there are fewer electrons, and the holes would want to diffuse over to the N side.
But if they did that, you'd get charge moving across.
Exactly. Electrons moving one way, holes the other, that's an electric current. But we know in thermal equilibrium, with no battery attached, there's no net current flowing.
So something must stop that diffusion.
Precisely. As the first few electrons diffuse into the P side and holes into the N side, they leave behind fixed, charged impurity atoms, positive donors on the N side, negative acceptors on the P side. This creates a layer of fixed positive charge and a layer of fixed negative charge right at the junction.
A dipole layer.
Yes, a fixed dipole layer. And this layer creates an internal electric field pointing from the N side to the P side. This field then opposes further diffusion. It pushes electrons back towards the N side and holes back towards the P side.
So the diffusion creates a field that stops the diffusion. It balances itself out.
Perfectly put. The mobile carriers get pushed away from the junction center, leaving this depletion region with the fixed charges creating the built-in field.
So at equilibrium, no net current flows. But it's not static, is it? It's a dynamic balance.
Exactly right. It's like a perfectly still pond, but underneath there are constant currents flowing that perfectly cancel each other out. Shockley describes two main components. There's a forward current. This is composed of majority carriers, holes from the P side, electrons from the N side, that have enough thermal energy to climb over that potential hill created by the internal field and diffuse into the other side. Once there, they diffuse for a bit, a characteristic diffusion length, before eventually recombining.
Okay, a flow over the barrier.
Right. And then there's a generation current.
Mm-hmm.
This is made of minority carriers, holes generated randomly by thermal energy on the N side, electrons generated on the P side. These guys see the field as a downhill slope, so they just get swept across the junction.
A flow down the barrier.
Exactly. And in perfect equilibrium, the forward current climbing over exactly balances the generation current sliding down. Net current, 0.
Okay, that makes sense. Now, what happens when you apply an external voltage? This is where the rectification, the diode behavior comes from, right?
This is the magic, yes. Applying an external voltage essentially tilts that potential landscape.
How so?
Well, let's say you apply a reverse bias. That means making the P side negative and the N side positive. This adds to the internal potential hill, making it even higher.
Harder for the majority carriers to climb over.
Much harder. The forward current, if, drops almost to zero. But the generation current, e.g., those minority carriers sliding downhill that's hardly affected by the barrier height, they just keep getting generated and swept across.
So you're left with just that small generation current.
Pretty much. This leads to saturation. The reverse current quickly reaches a small constant value and doesn't increase much even if you crank up the reverse voltage.
Okay, that's reverse bias. What about forward bias?
Forward bias is the opposite. P side positive, N side negative. This opposes the internal field, effectively lowering that potential hill.
Making it easier for the majority carriers to slow over.
Much, much easier. And because the number of carriers with enough energy to climb the hill increases exponentially as the hill gets lower, the forward current, if, increases exponentially with the applied forward voltage.
Ah, the exponential diode curve.
That's exactly it. Shockley presents the famous diode equation. The total current I is the saturation current, is times X, P, Q, V, KT1. It beautifully captures both the tiny reverse saturation current and the rapidly rising forward current.
And did this elegant theoretical equation actually match what they saw in experiments with those new pure PN junctions?
Remarkably well. Shockley shows experimental data for germanium junctions that fits the theoretical curve almost perfectly. And crucially, that factor KTQ, which is about 25 millivolts at room temperature, showed up directly in the data. The voltage needed to increase the forward current by a factor of E, about 2.718, was indeed KTQ.
Confirming again the charge of the carriers and the role of thermal energy.
Absolutely. It was a powerful confirmation that their model of the PN junction physics was fundamentally correct.
The lecture also briefly touches on how light interacts with these junctions, right? Beyond just creating carriers like you mentioned with deathnium.
That's right. As we said, photons with enough energy create electron hole pairs. If you shine light near a PN junction, those newly created minority carriers can diffuse over to the junction and get swept across by the built-in field, creating a current.
A photocurrent.
Yes. And they found that the current produced decreases exponentially the farther away from the junction you shine the light. This allowed them to directly measure that diffusion length, how far carriers typically travel before recombining. For good germanium, it could be around a millimeter.
Which is pretty far on a microscopic scale.
It is. And this effect, of course, is the basis for solar cells and photodetectors. Light acts like a current generator connected across the junction.
Okay, so with the PN junction physics beautifully worked out and experimentally verified, the path was clear for the junction transistor. This is really the heart of amplification, isn't it?
Absolutely. The junction transistor is essentially taking two PN junctions and putting them very close together, back to back, within that single crystal. You create a sandwich structure.
Like N-type, then P-type, then N-type again. An NPN transistor.
Exactly. NPN is a common type. Or you could have PNP. Shockley notes the strong analogy to the vacuum tube triode, which it was destined to replace.
How does the analogy work for an NPN?
Okay, think of the three layers. Emitter N, base P, collector N. The emitter acts like the cathode in a tube, emitting the charge carriers, electrons in this case. The collector is like the plate, collecting them. And the thin P-type base in the middle acts like the grid, controlling the flow.
So the input signal goes to the base.
Typically, yes. You apply the input signal between the base and the emitter. This controls the forward bias of the emitter-base junction, which in turn controls how many electrons are injected from the emitter into the base. The collector is usually held at a positive voltage relative to the base, creating a reverse bias across the collector-base junction.
And how did they physically make these tiny, intricate three-layer structures? You mentioned growing them.
Yeah, that was one way. During crystal pulling, you could carefully add impurities. Start with N-type melt, say, with antimony. Add an acceptor pellet, like indium, to briefly make the growing crystal P-type. Then quickly add more donor, antimony again, to overwhelm the acceptor and go back to N-type. Presto, NPN grown right in.
Wow, talk about precise control during manufacturing.
Incredible for the time. Another very common method, especially later, was using alloyed junctions. You'd take a thin wafer of, say, P-type germanium, the base, then place tiny pellets of metal containing a donor element on either side.
For the emitter and collector.
Right. Heat the whole thing up. The metal melts and dissolves a bit of the germanium underneath. When it cools, the dissolved germanium recrystallizes, but now it incorporates the donor atoms from the metal, making it N-type. So you form N-type emitter and collector regions alloyed onto the P-type base wafer.
Clever. So what's actually happening with the electrons inside an operating NPN transistor? How does the amplification work at that level?
Shockley uses a potential energy diagram for electrons, which is really helpful. Imagine the collector junction is reverse biased. For an electron, that looks like a steep downhill slide, easy to go that way.
Okay.
The emitter junction has a much smaller potential hill. Applying the input signal varies the forward bias across this junction, which effectively raises or lowers this small emitter hill.
Controlling how many electrons can get over it from the emitter into the base.
Exactly. Now here's the crucial part. The base layer is made extremely thin, and it's made from that ultra-pure material with very little deathnium.
So recombination is unlikely in the base.
Very unlikely. An electron injected from the emitter into the thin base finds itself surrounded mostly by holes, but before it has much chance to recombine with one, it diffuses across that tiny distance to the collector junction.
And sees that steep downhill slide waiting for it.
And zip, it gets swept into the collector. So a small change in the emitter barrier height, controlled by the input signal, causes a large change in the number of electrons successfully making the journey from emitter to collector.
Small input signal controls a large output current.
Yeah.
Amplification.
That's the essence of it. Maybe only 1% of the electrons recombine in the base. 99% make it to the collector. That gives you a current gain close to 100.
So how did this new solid-state amplifier stack up against the reigning champion, the vacuum tube?
Well, in terms of sheer voltage requirements, it was no contest. The junction transistor could be fully operational with voltages just a few times KTQ, maybe 50 to 100 millivolts. Vacuum tubes needed hundreds of volts.
Huge difference in power efficiency right there.
Massive, and that led to incredible flexibility in power levels. Because they needed so little voltage, and because those ultra-pure crystals had such low leakage currents, very little unwanted generation current from deathnium, a transistor could amplify signals using substantially less than a microwatt of power.
Tiny amounts of power.
Almost nothing. Yet the same basic device could also operate perfectly well at, say, 10 volts and 10 milliamps, handling significant power. That's a power operating range of maybe 100,000 to 1.
One device covering a huge range.
Incredible range, which led Shockley to predict something interesting.
What was that?
He predicted that because transistors were so flexible, electronics would need a much smaller diversity of transistor types compared to the huge variety of specialized vacuum tubes that existed then.
Fewer components, more streamlined design.
Exactly. He foresaw that a few standard transistor types could cover most applications, simplifying things enormously. And he was absolutely right about that.
What an incredible journey, from understanding these weird imperfections like deathnium, through devising experiments to actually watch electrons and holes move, to the elegant physics of the PN junction, and finally the junction transistor itself. It really hammers home Shockley's point, doesn't it?
It really does. That relentless pursuit of a practical goal, a solid-state amplifier, better telephone switching, directly forced them to uncover and understand entirely new physics.
The practical need drove the fundamental discovery.
Absolutely. And connecting this to the bigger picture, this whole story just profoundly illustrates how fundamental science, even when it's motivated by technology, can open up vast new territories. The ability they gain to control and understand things at this microscopic level in semiconductors, it utterly transformed communication, computing, everything.
And looking forward, in his 1956 lecture, Shockley was pretty bullish on the future, wasn't he?
Oh, remarkably so, and incredibly prescient. He actually quotes himself from his book published 6 years earlier, in 1950, saying, "It appears to most of the workers that an area has been opened up comparable to the entire area of vacuum and gas discharge electronics."
Basically saying this is as big as the entire electronics field that came before.
Yeah, a huge claim back then. He predicted countless unforeseen inventions based on carrier injection, the field effect, and significantly, he added that other new physical principles will also be utilized to practical ends.
Which certainly happened.
Oh, in spades, quantum effects, optical effects, things far beyond what they could fully grasp in 56 are routine now, all built on that foundation. His prediction was, if anything, an understatement.
So wrapping this up then, for you, our listener, what does reflecting on Shockley's perspective mean for how we think about innovation today?
Well, it really makes you wonder, doesn't it? In a world that seems increasingly focused on, immediate results, quarterly returns, very short-term applications, are we still creating the space, the environment that values the kind of long-term, curiosity-driven, fundamental exploration that even practical goals like Shockley's can inspire.
Are we potentially missing out?
That's the question. Are we missing opportunities for uncovering entirely new physics, whole new technological paradigms that might be hiding just beyond the horizon of the next obvious practical application?
Yeah.
Is the push for immediate utility sometimes blinding us to deeper, more revolutionary possibilities?
Definitely food for thought. Thank you for joining us on this deep dive into Shockley's work and the birth of the transistor age.
My pleasure.
We hope you've gained some valuable insights, maybe a few surprising facts to chew on. Until next time, stay curious.